We are going to take up one more problem on a simply supported beam, the problem number 19. Draw SFD and BMD for a simply supported beam loaded as shown in the figure. So in this figure, you can see there is a simply supported at both the point A and B, or the length of the span of the beam is 10 meters, where you have an uniformly distributed load between A and C for 20 kilonewton per meter for a span of 4 meters from A and C, E to C. Similarly, there is a simply supported uniformly distributed load of 10 kilonewton per meter for a span of 4 meters from the point B towards D. So now this is between D and B. Now so we have two support reactions. One is at A and the other one is at B. There are vertical reactions. One is RAV and the other one is RBV. So we need to find out the support reactions first. So to find out the support reactions, so taking the moments about the point A, so the sum of the clockwise couple will be equal to the sum of the anti-clockwise couple. So that means applying that, taking the moments about the point A, as RBV is going upwards, so naturally it will be in the counterclockwise direction. So RBV into 10 will be equal to, so then we need to take the clockwise. So since it is equal, so everything will going to get positive. So 20, so we have 10 into 4 into, so we are taking from here 10 into 4 by 2. So 10 into 4 and then open the bracket. Then you take the distance with respect to the midpoint. It is 4 by 2 plus that point is at a distance of how many meters. So from here 4 by 2. So you are going to get this distance plus this distance. It is 4 plus 2. It becomes 6. So 4 by 2 plus 6. Then close the bracket. Then you have plus 20 into 4 by 2. So RBV into 10 will be equal to 10 into 4 into open the bracket 4 by 2 plus 6, they close the bracket, plus 20 into 4 into 4 by 2. So on simplification, RBV, what we are going to get is 48 kilonewton. So reactions at the support, vertical reaction at the support B will be equal to 48 kilonewton. Now again, we have the sum of the vertical reaction which is going upwards will be equal to the sum of the vertical reactions acting downwards. So also that means we have RAV and RBV both are acting upwards. So RAV plus RBV will be equal to the vertical load acting downwards. So you have UDL which is acting downwards from A to C and also from D to B. So since it is only the loads we need to consider, so that means since it is a uniformly distributed load, it will be W per meter into length of the span. So W per meter is nothing but 20 kilonewton per meter. So 20 into the length of the span is 4. So 20 into 4 plus then again here in this case 10 kilonewton per meter. It is per meter is 10 kilonewton. Therefore 10 into 4. So 10 into 4 on simplification RAV will be equal to, that is 20 into 4 is 80 plus 40, it will becomes 120. So 120, you take RBV to the right hand side, you will going to get minus 48. So that will be equal to RAV will be equal to 72 kilonewton, which is so now the beam will going to be in the equilibrium condition. Now therefore RAV will be equal to 72 kilonewton. Now we will go for the first, we are going to take up analyzing individually. So we start from the left hand side towards the right. So first we are going to take between A and C, having a uniformly distributed load of 20 kilonewton per meter, wherein you have the vertical reaction which is acting upwards, which is RAV equal to 72 kilonewton. So then you have a 20 kilonewton per meter for a span of 4 meters. So we're going to consider this and we'll try to analyze this. So what will going to be the shear force at the point A? The shear force at the point A will be equal to, the load is acting upwards, it is positive, so plus 72 kilonewton. So as we are considering the shear force at the point C, which will be equal to plus 72 minus 20 into 4. Minus 20 into 4 plus 72, which will going to be 72 minus 80, it will going to become minus 8 kilonewton. So once you get this, so then what happens? The shear force changing its sign from positive to negative. So we can see the shear force is at point A, which is 72 kilonewton, from 0, you take up to this point A is 72 kilonewton because the positive acting upwards. So from there, it drops down to minus 8 kilonewton at the point C. And by doing so, the shear force changes its sign from positive to negative somewhere between A and C. We don't know what is that point, which will going to be found out. Next, what will going to be the bending moment? The bending moment at the point A is 0. So Bm at C will be equal to, so now as the load is acting upwards, it tries to sag. So therefore it becomes positive. So 72 into 4 will be 72 into 4. As the load is acting from the top, that means it is going to hog. So it becomes hog, the bending moment becomes hogging. Since it is hogging, it will going to become negative by sign convention. So that means minus 20 into 4 into 4 by 2, because we are considering the bending moment at the point C. So which will going to be at the midpoint. So again, so on simplification, what you will going to get is plus 128 kilonewton meter. So we start from the bending moment at the point A as 0 and bending moment at the point C as 128 kilonewton meter. And we cannot join between these two. That is basically because since the bending moment is changing its sign from positive to negative, so there will be a possibility of having the maximum bending moment. So that we will try to analyze after doing all the points analyzed. Now we will go for the next consideration. We are up to D now. So we have the vertical reaction at the point A, and then you have UDL up to C of 4 meters of 20 kilonewton per meter. Then we are going to have the point D, where there is no load between C and D. We are going to see that. So SF is constant at minus 8 kilonewton between C and D, as there is no other load is acting on the beam. So what is the shear force at the point D now? The shear force at the point D will be equal to plus 72 minus 20 into 4, which is minus 8 kilonewton. As there is no load between C and D, it remains constant of minus 8 kilonewton. So that is what we are going to get in the shear force diagram. So here you are going to get this point SF at the point C will be equal to minus 8 kilonewton. Between C and D, as there is no other load which is acting on the beam, so it remains constant, which is at 8 kilonewton. Now we will going to consider bending moment at the point D. So the bending moment at the point D will be equal to 72 into 6 minus 20 into 4 by 2 plus 2. So that means 72 into 6 minus 20 into 4 by 2 plus 2. So on simplification, you will going to get it as plus 112 kilonewton meter. So once you get this, so we need to plot. So to plot this, so further when you have from C to D, so there will be a slight decrease in the bending moment. So that means it becomes a linear curve. Then what will going to be the bending moment at the point B now? So for that, first we're going to consider the shear force at the point B. So what is the shear force at the point B? So between D and B, as there is a uniformly distributed load over a span of 4 meters of 10 kilonewton per meter. So since it is 10 kilonewton per meter, so it will be SF will be equal to minus 8 minus 10 into 4, because it is acting from the top, acting downwards. So minus 10 into 4, so it becomes minus 48 kilonewton. So as SF varies from minus 8 kilonewton to minus 48 kilonewton, according to the equation of parabola. According to the equation of the straight line, that is basically because you have W into X for a uniformly distributed load. So therefore, from the point D to point P, so it starts from minus 8 kilonewton, drops further down to minus 48 kilonewton. So, and this variation from minus 8 kilonewton to minus 48 kilonewton is joined by means of a straight line, which is equation of straight line, because the power of X is 1. Now, bending moment at the point B now. So the bending moment at the point B will be equal to 72 into 10. 72 into 10. Then we have minus 20 into 4 into, open the bracket, 4 by 2 plus 6. 20 into 4 by 2 plus 6, and close the bracket. Again, you have minus 10 into 4 by 2, which will be equal to 0. So once you get this, so here what we need to do, so bending moment at the point B will be equal to 0. So now once from 112 kilonewton meter, it drops down further to 0. So since it is a uniformly distributed load, so you will going to get a parabolic curve because the power of x in this case is w into x by 2. So w into x by 2, it becomes x square. So naturally, since the power of x is 2, therefore the variation from D to B will going to be a parabolic curve. So where we are going to get the maximum bending moment? So the bending moment we are going to get at the maximum when the shear force changes its sign. So the shear force changes its sign at the point E. So therefore, which is at a distance of x meters from the fixed end A. So the maximum bending moment occurs at a point where the SF changes its sign. So let E be the point at a distance of x meters from A, where the SF changes its sign. So what is SF at E? SF at E will be equal to, that is 72 into x minus 20, 72 minus 20 into x. 72 minus 20 into x will be equal to 0. Therefore, x will be equal to 3.6 meters. So from the bending moment or the shear force changes its sign at a distance of 3.6 meters from the end A. So now what will going to be the maximum bending moment? So the maximum bending moment will be equal to 72 into x minus 20 into x by 2. So since the value of x is 3.6, so what you are going to get? So you're going to get it as 72 into 3.6. Substitute the value of x as 3.6 now. So that means 72 into x. So that means 72 into 3.6 minus 20 into x by 2. So 20 into 3.6 into 3.6 by 2. So that is what we have done here. 72 into 3.6 minus 20 into 3.6 into 3.6 by 2. On simplification, you will going to get it as 129.6 kilonewton meter. So now we got the maximum bending moment at the point E. So from here you draw a line, and so that you are going to measure the distance of 129.6 kilonewton meter and join this 129 and join this 129.6 kilonewton meter and also this 128 kilonewton meter by means of a parabolic curve, because the power of x in this case, it is a w into x by 2. So it is x square by 2. So naturally it becomes the power of x is 2. Therefore, you will going to get this as a parabolic curve. So this is how you will be able to analyze the shear force diagram and the bending moment diagram for the simply supported beam with the uniformly distributed load between A and C, and also again uniformly distributed load of 10 kilonewton per meter between D and B. So this is the final solution. Thank you.